Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Just so you know where we are, we're finishing up a couple of generalities about multivariate distributions, and then we'll be going on to what's effectively part of the same area, which is how to transform distributions from one distribution to another. You might say, why are they related? Well, often if you're transforming a distribution, you can just transform one dimension to one dimension, but then we'll do some more complicated cases that are effectively transforming two dimensions to two dimensions, and in that case it's effectively just an image of a multivariate distribution under various functions. So that's why they're related. But for the moment, let's finish talking about multivariate distributions. And what I wanted to talk specifically about, apart from a couple of examples that we'll do in quite detail, which are multinomial, which is an extension of the binomial, and multivariate normal, which is an extension of the normal. They're probably the two most important in the discrete and continuous case respectively. Before we do this, I want to talk about conditional expectation, because this is really a big subject. Okay. And so conditional expectation. We already talked a bit about conditional distributions. So the conditional distribution, as you recall, and I'll just do everything in the bivariate case. There are concepts that have very wide applicability, but if we stick to bivariate, then everything will be simple. So it's described by, it is a distribution, by the way, the conditional distribution, and let's say this of x given y. Now, the exact definition depends on whether discrete or continuous, and I've sort of alluded to the fact that there's even, there are those examples that are degenerate, like where, there's a linear relationship between x and y, and those are not going to be covered here unless it's discrete. So the continuous degenerate case, there actually is a perfectly good theory of conditional expectation and all that. It's just, we don't want to do 10 different cases, so we'll stick to the most common cases, and the more general theory can wait for a more advanced probability course. But anyway, so the conditional distribution of x given y, in the discrete case, this was the best way to characterize a discrete distribution, as you know, is not the CDF, but the PMF. So that's the conditional PMF, which I write Px given. Now I used to write it, oh look, I'll keep doing it this way. The because this is there's nothing wrong with conditioning on the event y equals y, so long as that actually has a positive probability, which is what tends to happen in the discrete case. This is, as you recall, so conditional equals joint over marginal. If you never remember anything else, dy over y. And to remind those who've got how to get the marginal from the joint, if I just want to know the chance that y lies at a particular value, what do I do to all the joint? An action. What do I do to them? Sum them all up. Yeah, sum over all possible values of x. Okay, and the continuous. So this is all review from last time. That you do the same with conditional density. And density, now I tend to write it this way because there's no real meaning to actually conditioning on the event y equals y. That's an event of probability 0. There was that quote of Kolmogorov. It's not an admissible concept to conditional on an isolated event of probability 0, but it is admissible to conditional on a variable being a particular value when that variable is continuous, or even more general cases, because that variable gives you more information than just some event. I'll talk a little bit about the famous paradox to do with that in a moment. But so once again, it makes a lot of sense. It's just the density divided, the joint density divided by the marginal density. And you can imagine, if you like, a continuous thing being divided up into lots of little squares, and then the probability mass function would be roughly equal to the density times the area of the square. So these things are just related by you could approximate the continuous case by the discrete case, divided by fy of y. And of course, these things are defined only at the points where the denominator is positive. So you have to have, in the discrete case, you have to have mass function positive there. Continuous case, you have to have positive density there, even though the probability of actually lying there is simple. Okay, and to remind us how to get the marginal from the joint, what is the verb? What do I do to it? I can't sum them. I have to integrate them. I'll write minus infinity to infinity. Of course, if you have a restricted range, then you just substitute in the appropriate range, which may depend on the particular y choice. That's if you have different cross-sections, if you have different slices at different kind of intervals of different heights, it's quite possible for the range of integration to end up depending on which y slice you take. And of course, I've got to say dx. So that's how you get it. Okay, that's the conditional distribution. It's perfectly good distribution. I guess I didn't prove it, but it's very easy for you to check that when you integrate that up, it integrates to 1. When you sum that up, it sums to 1. And it's perfectly well defined. I said there was a little bit of an asterisk about the exact meaning of this in cases where the joint distribution is not continuous. Really, this is something that can be totally ignored, just in case you were wondering what that was all about. Just imagine a density that was, let's say these are squares, and I have density I have some lower density here, just constant, and then I have a jump to a much higher density here. Doesn't actually matter what it is, but so long as that's your joint density function. Turns out it's a little ambiguous what does it really mean to talk about the density along this slice, because it could really be chosen to be the same as, the conditional density here is uniform. The conditional density here is not quite uniform because it's more likely to be in the middle than it's likely to be there. What exact choice you make on that line, there will be two choices. So really you should ignore this picture, except that when we say that the conditional distribution is well defined, there's kind of slight choices when there's jumps in the joint density function. But rarely, usually we don't have too many jumps in the joint density function. And regardless of which choices you make, the key feature, so although there might be slight choices involved, it actually doesn't matter. So the things you might be worrying about is, do I include less than or equal to or less than when I define the joint density functions? Strictly less than or less than or equal to. My answer to that is don't worry. Although they might define slightly different functions, all the properties will be the same regardless. Okay, so let's talk about those properties. Before I talk about the properties, I really want to talk about conditional expectation. While it has a very general definition in probability theory that covers all these cases and many, many more. I'm not going to focus on that, I'm just going to give you the discrete and continuous definitions. And you should agree that they make sense because they're simply taking expectations with respect to these distributions. So if I have, once again, a variable x given y, the x given y equals y. Let's do this first in the discrete case. I can write a conditional expectation in either case. In the discrete case, there's absolutely no problem with doing this. It's sum of the possible x values taken. I sum all the possible x values times their probability, and the probability is just this discrete probability x given y equals y. So there should be no surprises reiterating what we already know, but with a conditional distribution. In the continuous case, I would integrate over all possible x values, x, f, x given y, of x given. So nothing other than what you expect. So I've sort of, you'll note that I've actually done this notation. Even when the probability of y equals 0, we still use this notation just because there's not really a great other notation. But there is a more interesting thing called conditional expectation as a random variable. Okay? So this will be, so that I'm actually having two different notations, x given y. So this is not the same thing as that. Is the random variable you get, because just note that if I've got lowercase y there, that might be, for instance, lowercase y equals 10. So this is a specific number, right? I can calculate a specific number here. It's not a random variable, it's deterministic. That's, a very precise thing. But expected value of x given y, the random variable, is not a number. It's a random outcome, but it is a random outcome that depends only on y, not on x. That's the way you should think about it. And what it is your best guess of the value of x given what you know about y. Okay. So, but more formally, how do you get it? By taking the function. Remember, that's an ordinary function. Expected value of x given y equals y, and substituting in. Subbing in y, which is the variable, equals capital Y. So this seems totally counterintuitive. First I have conditioned on making y equals some specific value lowercase y, and then I've gone somehow backwards. I've substituted back in y equals the random variable y. Now I don't get back to x itself. The reason is you lose information. When you do this, I've got all this information in a two-dimensional structure here, and x and y could be anywhere that they are. Now, when I take the conditional expectation of x given y equals y, that will be, I'm going to roughly, assuming that this, you could imagine the example uniform on a region R. We talked about that example last time, where that's a perfectly good bivariate distribution. It's uniformly likely to be anywhere in this region. Now, the conditional distribution along each of these lines is uniform, so because you're equally likely to be anywhere along the line. The marginal is not uniform, but the conditional is uniform. And so this is what you get expected value of x given y equals, let's imagine these have values 1, 2, 3 on the y-axis just for simplicity. So this is the y-axis. Then the conditional expectation that x given y equals 3 would be this one number here. This would be the conditional expectation of x given y equals 2 would be that one number there. And this would be the conditional expectation of x given y equals 1. Now, what is this strange object here? That's not any specific number like those three. It's actually a random variable that gives you something along that line. So it would actually, you get some kind of interesting mid. If you traced out the conditional expectation function, right? I can take the conditional expectation of x given y as a function of y. I've drawn it there. Now note, it doesn't actually extend below the bottom or above the top. That's because you're not allowed to evaluate a conditional expectation when the density is not positive, the marginal density is not positive. So it's not well defined in a region where the random variable never lands. But it is well defined here, and that's what it looks like. So that green thing, in case anyone was wondering, is the curve. That is nothing other than the curve. It's x as a function of y. Lowercase x equals the function of y given by expected value of x given y equals y. Okay? So that's a function of... For the moment, this will not be a general notation. For a moment, I just want to call that g of y, just to remind you that that is a function of y. X equals g of y. And then, so just to remind you, if this is the function g of little y, expected value of x given that y value, and then what is the expected value of x given y? It's nothing other than substituting in capital Y instead of little y. So it's a function of a random variable. The function is the conditional expectation function. You substitute in the random variable y, you get that. Now, it is not the same as the original value x. The reason is information has been lost. So if you plotted x and y together, you always get something in this blobby region. Whereas if you plotted x, comma, if you plotted, g of y, comma y, which is conditional expectation of x given y, comma y, it would always lie on this curve. Because the conditional expectation of y given y is determined by the y value. It's random, but it's random only in as much as it depends on y. It does not have any further. So it has lost information. So yeah. That's conditional expectations of random variable. And why is that an important concept? Well, for those who are interested, this is well defined as a random variable, even if there were minor choices. This is really so unimportant that I don't want to emphasize it. Going into the definition of the joint of the conditional density x given y. There was, sometimes very slight variance you could choose there. Regardless of which variant you chose, you would always get the same conditional expectation as a random variable. Okay, and there is this great rule. I've often called it the Tower rule or the Tower law. That's kind of a quick way to say it. And another name for it is the law of iterated expectation. And this is the most important property of conditional expectation. What it says is that you have x, and you take its expected value given y. Now that's the conditional expectation as a random variable. It's itself random, but it's random only depending on y. It doesn't have all the extra information of where the x coordinate was. It's just your best guess of where x was given y. And I've traced that best guess here. Right? So if you know that y is 1, your best guess is here. If you know that y is 2, your best guess is here. Plug in the random y. It's just a random variable. Now, I want you to know that this random variable is not as widely dispersed as x itself. The reason is you've lost some of the variability that is due only to x alone. So the random variable x can lie anywhere from here to here, right? Anywhere on the left or anywhere on the right. The random variable expected value x given y only lies between here and here. All the extra variability that is due to x, absent y, has been removed. So all you have is the variability due to where y is itself. So if y is down here, the conditional expectation is here. And so this is a less variable if I were to take the variance of this random variable, it would be lower than the variance of x. We'll even get a more precise statement about that later. But what about the average value of this? You would think if at each particular y value I've averaged out the x variability, and then I've got a random variable, and then if I average those all out themselves, this is a random variable, you can always take expected value of try to take expected value of a random variable. If I took that, surely that should lie at the centre of mass of x in the first place. Surely that should be exactly the same as the expected value of x. And that is true. It's an absolute theorem. It's true discrete, it's true continuous. In fact, it's true for every pair of random variables, including cases we haven't covered. This is the fundamental key feature of conditional expectation. And so the meaning is if you first partially average out over all you might call this the idiosyncratic variability in x. The variability in x that is just due to x itself, even keeping y constant. You average out over all that idiosyncratic variability, then you average out over all the variability due to y, and that's the same as just averaging the variable in the first place. Okay. So I guess probably I'd better give a proof of this in the, let's try it in the continuum case, if that's the tricky case. Let's just use the formulas that we've got. Expected value of x given y is, of course, integral. I always write minus infinity to infinity and assume that the constraints are kept within the density itself. So f x times conditional density. I'm straight away going to substitute in joint over marginal. As I said before, if you remember nothing else, conditional equals joint over marginal. Same for mass function, same for density. I have to integrate out of those things. So expected value of that's y equals little y, sorry. Okay. Of x given y. And you remember I sometimes called this thing g of y. Right? Is reminder, this is the random variable, and the meaning of that is g of capital Y. Right? That is the meaning of conditional expectation as a random variable. And that means, so, the expected value of that random variable, x given y, equals expected value of g of y. Now, what can anyone remember about taking expected value of a function of a random variable? We did talk about this in the context of just expectation earlier. Do you have to derive the distribution of g of y to find this expectation? You do not. That's the key thing. Sometimes people think, oh, I need to go to chapter 6 and look at transformations to do this. You don't. Okay? It's much simpler. You just add up all the, or in this case integrate, all the possible values that it takes, which are g of y, times their density. Times the density fy of y. You see that? We're doing it with respect to the random variable y. Y has a density, which is its marginal density. And then I multiply that, if it was just expected value of y, this would be y, and for y of y, dy. Here I'm not doing expected value of y, I'm doing expected value of a function of y, so I substitute in function of y, density of y, dy. Okay, once again, minus infinity to infinity. And then, so that is equal to integral minus infinity to infinity. I have to, first of all, what is g of y? It's this long integral. And then I have to multiply by fy y equal. So you can see that, well, the first thing, before I do anything hasty, I should make a little claim that we can swap the order of integration. Now, in general, this is something you have to worry about, especially because x can be positive or negative. I'll just say, in this case, it's true, and I should say so long as, I'll even change my statement here, so long as the expected value of x exists. So you remember, if that's a positive variable, it has to be less than infinity, and if it's positive and negative, then both the positive part has to be less than infinity and the negative part has to be greater than minus infinity. So clearly it wouldn't make sense to talk about this if the expected value of x didn't exist, but I guess it's not true in that case. So it follows from expected value of x existing. Okay? Often the fact that expected value of x exists is written that the expected value of absolute value of x is right. Anyway, this isn't a maths course, so I won't obsess about that. So if we do swap the order of integration, you then get, I can of course bring this factor in here where it will cancel with the denominator. I can bring a constant factor from outside an integral within the integral. That's always true, because it's constant within the integral with respect to x. And then all I'm left with is x, f, x, y, y. I swap the order. And it's actually, I know maybe I need that for some other arguments. I not necessarily need that here, because that is actually the definition of expected value of x. If you don't like the fact that it's the definition of expected value of x, then let's put in. I'm going to put in an extra step for those of you who don't like that jump. And okay, this extra step will now use the fact that we've swapped the order of integration. So it wasn't useless. Once I've swapped the order of integration, you see, by putting the fy of y in there, I cancelled that with the denominator. The fact that I've now got dy dx means I'm allowed to move x out the front of the integral because x is constant with respect to y. So that says I have integral minus infinity to infinity x times minus infinity to infinity f x y x y dy, and then times here. So the final part of the proof will be finished once we realise what is the integral out of the joint density along one axis? Marginal, exactly. So that is marginal density of fy of y. X of x, sorry about that. I integrated out the y, and therefore what's remaining is the marginal density of the x. So integral of x, fx of x, dx of x. Okay, so yeah, so it was worth doing the swap of it. Okay, so that's the end of that proof. As I say, it's not really a class that obsesses about the proofs given in class, it's more the methods. So let's go on from that, and it seems like an odd thing to make so important. But let us now talk about variance of a conditional expectation. And I guess that's, just before I go on to say that, I've been emphasizing the fact that this notation, and just remember that we might have been vague before, but this notation means something totally different from this notation. That is a number, that is a random variable. It's a random variable obtained by substituting in, consider this a function of y, and substitute in the random variable y. So while it is a function of y, we consider it as a random number. So, and it's never going to be the same as x itself, except in one special case, which is where x was fully determined by y. That sometimes happens, like in a case of, for instance, a correlation of 1 and a correlation of minus 1 means x is totally determined by y. In that case, this will be the same as the variable you started with, e of x. And that's the case where the progressive loss of information actually is not a loss of information in the first case. The way you should think of law of iterated expectation is a progressive loss of information. This is losing all the information at once, just blur it all in one, shake everything up together. This says first shake up everything within the strips, within y equals a constant. That's expected value of x given a fixed value of y. And then average that over all the y. So it says that if you average in one way and then average over all of those, it's the same as just averaging everything in the first case. Okay, so variance of the conditional expectation. Well, the theorem in this context that I'll say, as I said, the variance of conditional expectation is actually going to be less than of the variable you are taking expectation of. That's because you've lost variability and you've lost information. It can't go as far. Oh, okay. It could be equal, in which case you've not lost any information. So let's make this more precise. The variance of x and this is just a great formula, I love this. It's first of all the variance of the conditional expectation plus, so this is so much so plus something positive. That's what I was saying before. The variance of the conditional expectation is lower than the variance of the variable you started with, right? Because you've lost information. Let's always have this picture in mind. You know, conditional expectation only varies along the green line, not so far left or right. The other one's much bigger. But then what is the difference between them? And it's just great for, you know, aesthetically, this formula, plus the expected value of the conditional variance of x given y. So, variance of x is variance of expectation of x given y plus expectation of variance of x given y. Great formula. By the way, what you can probably guess, but what does it mean to say the variance of x given y? Same thing. Okay, so I'm going to have to do the same thing as in the case of well, it's really nothing surprising. Expected value of I have to take something squared. The I don't have enough space on this line. It's what you'd expect with these conditional variances. So conditional on y equals y, I have to take conditional on y equals y, I have to take the square of the deviation. So expected value of x minus its expected value given y equals y. Square. So this is, you do everything in y equals y world, right? So I have lots of, so it's just taking that horizontal cross-section y equals y. On that horizontal cross-section, I take the variable itself and its mean on that cross-section, and I square it, I take the expected value. So that is, of course, another way to say that is that is the expected value of, there's always this calculation formula, x squared given y equals y minus, okay, I'll let you do all the others to figure this out, minus the expected value of x given y. So that's what the conditional, and variance, sometimes that's just a constant because I did y equals y, and the variance of x given y is the same thing with random variable involved, so expected value of, I'll give you both formulas again, x minus the expected value of x given y squared given y, which is, of course, the calculation formula tends to be second moment minus first moment, so expected value of x squared given y minus expected value of x given y squared. So a lot of formulas there, but they're what you would expect from the definition of expectation, and the fact that this is something that we want to do for conditional on y equals y. Okay, so let's give a proof of that. We won't have to go through integrals to do this proof, of course. In case it wasn't, in case people were worried about the fact I just did this with integrals, replace every integral with a sum in that proof and you have the discrete case proof. And it's actually true more generally, but since we're not worrying about that cases, we won't worry about that. So the proof of the variance of, okay, so let's just write variance of x is, of course, expected value of x minus value of x squared. Okay, so let's try and break this up into two different parts. Expected value of x minus expected value of x given y. Now remember that is a random variable plus expected value of x given y, expected value of y. So we're just going to break it up into two parts. Firstly is how far do you differ from the cross-sectional mean, which is, I first take how far are you from here, and then how far is that cross-sectional mean from the true thing. Those are the two parts, and that should be expectation. Okay, so it's a classic trick when you're doing this. So expected value of x minus expected x given y squared plus 2 times the expected value of the product x minus expected value of x given y, expected value of x given y minus expected value of x plus expected value of x given y minus expected value of x squared. So all I've done is I've taken the part that was to be squared, and I've done a plus b, and I've said a squared plus 2ab plus b squared. Okay, so that's expected value of this thing squared. So that is this is actually going to be the opposite order around from what we did before. So what I'm going to tell you is going to happen. This term is going to end up being 0. Maybe I won't go through the full justification of why that is 0. But essentially, expected value of x minus, if you just ignore the right-hand factor here, x minus its horizontal mean, that conditional on y, that expectation is 0. So if you actually apply the Tower rule to this term, you'll find that conditional on y, that expectation has to be 0, and therefore the whole expectation has to be 0. So maybe this will be a proof sketch. It won't have all the details in it. I might provide those later. But and then this term is going to end up being equal to the expectation of the variance of x given y. And this term is going to end up being equal to the variance of the expectation of x given y. Okay, I don't want to take up the whole time doing this. So there's actually about several applications of the Tower rule, both in saying that this is 0, saying that that one is that, and saying that that one is that. So maybe I'll leave that either as an exercise of the Tower rule, or I might talk about it a little later. But the concept is quite simple. There's an extra, there's an extra term as to how variable x is compared to its conditional expectation. It's got a beautiful formula, and we'll just leave it at that. So let's go on, and I really want to do, before we go on to transformations, I want to talk about 2 really important examples of multivariate distributions. And the first one is really easy, but it's worth doing anyway. So multinomial. And this is good because it's a multivariate example, not just bivariate. So multinomial. And it's going to have P1 up to Pn. Now it's quite important here that P1 up to Pn in principle should add them all up. You should get 1. Now if you don't, it's much like what we were talking about with categories, and this is back to combinatorics almost. This is counting. These are discrete random variables. They count how many of a experiment, and I should say, okay, forgive me here. N is so sacrosanct as the sample size that I'm going to have to put an N as the sample size, and not only that, I'm going to have to change this to either K or N. Let me just say K because the difference spoken between N and N is not very high. So I'm going to have P1 up to P10. Sorry about that. There'll be K categories and N samples. So Xi is the number of samples or number of trials of that land in category I. Okay, so there are K categories. So there are N IID trials. Each one lands in one of K categories. So it's like binomial, which is yes or no. Lands in category I with probability P pi. So that's clear enough. that's why they have to add to 1. You know, you just do a try. It's like a three-sided coin. You know, it lands in one of the 3 categories, and each of them has a probability. So it's quite simple. And by the way, there would be kind of a hypergeometric variant of this. Sampling without replacement would be very complicated, and let's not worry about that. We've implicitly talked about it in some of the earlier examples, but that sampling without replacement, as always, is much more complicated. So let's just do the sampling with replacement case where they're I-ed. Okay? So if number of trials land in category I, then the whole point is that these have a joint distribution. So I can already tell you that the marginal distribution of xi is given by, well, I'm going to say it this way. Xi is, remember, if you take them as a joint, it's multinomial. But if I'm just counting how many trials land in a fixed category I, what type of distribution? Binomial, because each is either a yes in category I, binomial, and pi, right? It's a yes with probability pi and then no otherwise, because then it's not the category I. So that's so far so easy. The joint distribution is of course multinomial. Just to reiterate, np1 dot pk, and I may as well give the mass function. P x1 xn of the sorry, k, there are always k categories, is equal to, well, it's great that we did the multinomial coefficients, because out of n, I'm going to have to choose x1 to be category 1, x2 to be category 2, and xk to be category k. So, great, we did multinomial counting, right? That's how many ways you can choose them to be in that category. But of course, then you have to have the probability that you actually had x1 of the p1s, x2 of the p2s, xk of pk. So that's what those are, and they must add to 1, provided, of course, that these ones add to 1. If they don't add to 1, then you really ought to add an extra k plus 1 category, which mops up all the extras. Right? If the sum of the probabilities is less than 1, you just add another category. Okay, so that's the joint distribution, and the only thing, so we already know, I'm not sure whether I emphasised a lot about covariance. It's just a way of measuring how one variable varies against another. In case anyone missed it, covariance of x and y is of course the expected value of x. Now everything is centered, which means you take it away from its mean, y minus the expected value of y. That's all it is. Now, once again, you can do algebra and take this is the expected value of the product minus the product of the expectation. Okay, so that's easy enough. And the correlation coefficient between two random variables is nothing other than the covariance divided by the product of the standard deviation, square root of x. And the great thing about this is it's in -1 to 1. That's actually, if you want to talk about it mathematically, that's the Cauchy-Schwarz inequality. It says a sum of products is less than or equal to the square root of the corresponding to sums of squares. Or better to say it in geometric language. Covariance, by the way, is a dot product. If you do that out in kind of coordinates, it's like there's a dot product between this vector and that vector. This is just the dot product of x with itself, the dot product of y with itself. So this says that the dot product between two vectors is less than or equal to the product of the two Euclidean lengths. And that better be true, because the dot product's meant to be length times cosine theta. So all of this is related to that geometry. So yes, covariance and then correlation coefficient always lies within that. And it's a very special case if it's one that they must lie on a positively sloped line. It's -1, they must lie on a negative sloped line. So let's just do that in the case of, we already know, of course, the expected value of xi is npi, and the variance of xi equals npi 1 minus pi. So we already know that. So all that we haven't done is the covariance of xi with xj. So that was an aside about covariance in general. Back to the example. Covariance of xi and xj. Well, it would be nice to find a way to do this that didn't involve adding up across all of those things. At least we can use the product formula like that. So let's possibly on the next tutorial, or maybe a bit later. So it turns out to be minus n pi. Okay, maybe that's easy to see, or maybe it's not. So actually, what I would recommend as the best way to do that is you could write xi, always the indicator function method. Okay, I'm not going to write it up how you want to do that, but the method I recommend to do is, rather than going through that, I always hate doing calculations involving multinomial coefficient. You get, factorials and unwrapping and very unpleasant. So much better to use the indicator function method. I'm going to plug this from before. Indicator function method. Xi is of course some j equals 1 to k of indicator that j equals 1 to n. The indicator that role j is category I. Right? It counts the number of roles that are in category I. You can imagine a die or a D20 or something like that. And then expected value of xi, xj is then going to be the expected value of sum of something times sum of some indicator functions, sum of some other indicator functions, blah, blah, blah. Okay, so you'll get it a lot more simply by doing that than you would by going through the joint PDF. So that PMF is often quite unimportant. So the last thing I wanted to talk about is multivariate normal. And for the moment, let us worry about bivariate normal. There's enough complications with that before we go on to talking about general limits. The bivariate normal, standard, and this is a review of the standard normal in one dimension. F z of z. So far we use the lowercase pi of z is equal to e to the minus r z squared divided by square root of 2 pi, and that's the interesting constant that makes it integrate into 1. We already know this. Now, normals end up having a lot of geometric properties, a lot of kind of linear algebra properties, and we're going to find out some of those. But the first thing that we know about, so bivariate normal is more general, just the independent case. Two independent standard normals. Okay? And I'm going to call them Z and W because I want to keep X and Y for some other. So they're both independent. F Z equals F, W equals Y. Okay? So Z independent of W. So the first thing is let's use our knowledge of multivariate distributions to talk about the joint density function of Z W. Does anyone know how to write that down? There was a fact I said about independence before, which is actually any of these things that you want to characterize the distribution by, PMF, PDF, or even CDF, so mass function, density function, or cumulative distribution function, all of them have the product property in the case of independence. So I simply multiply the Fz of z times Fw of w. By the way, if you, this is an aside, but compare the non-independent case. Okay? The non-independent case for any variables Fzw is Zw. You can still start by writing Fz of z, and then you just recall what is the conditional density, Fw given z of w given z. Right? That's actually true whenever you have a pair of joint normal random variables. The joint equals the, conditional equals joint over marginal. So joint equals marginal times conditional, if you do it right. And the only difference in the independent case is that conditional equals unconditional.